All right, we will go ahead and get started. And for any late stragglers, they can just kind of play catch up here. Thanks everyone for joining. I'm going to go ahead and I'll let everyone here know. I might reiterate this as we get a little farther in if we have a lot more people join. But the polling or the questions and answers, there's a Q&A tab. So if you have any questions throughout the presentation, just go ahead and type them in right there. And at the very end, I've left some time for us to go over them. So pretty short presentation today, actually. This is actually my first time giving this one. So this is part of our new Advanced IQ module. So basically continuing education with our products. This one specifically is going to be talking about charge, the state of charge, discharging, and really just these characteristics of the lithium iron phosphate battery, and specifically the SimpliPhi battery, and how to kind of use those to your advantage. So without further ado, I will hop right into this. So we're going to start with the Phi charge characteristics. So this is kind of the base of the charge here. This is our charge curve. This one, even a little bit outdated, still working on getting some new charge curves, but basically it's still virtually the same. This is a controlled charge curve. So one thing I'll reiterate kind of later on down the line is this is a bit different than what you might see in the field, but this is what we see in the lab when we're testing the batteries. This is the voltage over time and how the battery actually interacts with charge. Okay, so let's start with C over 2. And really what I'm talking about here is we're talking about current. We're talking about charging and how ampacity, what you're putting into the battery really affects it. So the C over 2, in this case, we're talking about basically 2 being 2 hours, the time. I'm sure for anyone that's taken any of my other presentations, webinars, anything like that, has heard me talk a lot about C over 2. So in this case, we're just focusing on the maximum charge, that C over 2. This is the maximum amount of current we can put into the battery, each individual battery that is, at a continuous rate. So meaning if we have we'll just go to these examples actually right away. So the max charge of a 2.7 and our 3.5 kilowatt hour batteries at 48 volts. So the examples here would be the 2.7 kilowatt hour battery can actually handle 26 amps DC, and the 3.5 kilowatt hour battery can handle 34 amps DC. So this is continuous power. This is not surge. We will get into that in a little bit. So, convenient thing you can do here is whether we're talking 34 amps DC or if we want to just convert it into what's the maximum capacity as far as continuous power that the battery can perform in kilowatts. So if let's say the 3.5, instead of 34 amps DC, we could think of it as 1.75 kilowatts continuous for 2 hours. So obviously, if the battery is only 3.5 and you're discharging 1.75 per hour, it's only going to last 2 hours, but that is the maximum discharge continuously of the battery. So there's some things to think about here when we're talking kind of the nitty gritty, and this is really what this presentation is. We're really trying to dig down how this actually plays out in the real world, how it affects the installations, and what we can really kind of look at as far as those things go. So oftentimes when we have an installation, let's say maybe a residential, maybe off-grid, on-grid, doesn't really matter. We often run into multiple charging sources. So it could be anything from a PV source, a wind source, generator, grid, whatever it may be. We oftentimes need to kind of consider that even though the PV is sized to 1.75, or maybe it's the charger is limited, which we'll talk about here coming up, if we want to make sure that these charging sources are not going to run at the same time. And if they are, we do want to make sure that we're limiting the charge rate, again, to that C over 2. So if you have, let's say you have one battery so we're talking 1.75 kilowatts. I know that's a bit of a dramatic example. Most systems are going to have more than one battery, but let's just say for sake of ease and my awful math skills, let's say we have one 3.5 kilowatt hour battery. Let's say we have, so that's 1.75 kilowatts continuous the battery can handle. Now, if we have, let's say 1.75, let's say we have 1.6 kilowatts of PV, and we have a 5,000 watt generator running through an inverter that can output as well let's say 1.8 kilowatts. Well, the issue is even if we limit those both, if we do see both turn on at the same time, we could overcharge the battery just because it sees that the max charge is going on. Now, the good news, most systems, most inverters, most chargers are way more intelligent than that. They know when things are going on, like multiple sources charging, and there really wouldn't be a reason why your generator's running while your PV's max output's happening. Mostly if the PV starts kicking back in, now the generator can cool off. So there are things to consider when kind of looking at the system though, but definitely for the most case, you're not going to need to worry too much about multiple charging sources running at once. If you do have a system that is set up to have that kind of function, just keep this in mind again, that we want to limit it so that both charging sources add up to that max continuous, no matter how many batteries we have. So if we have, 5 batteries, then we would just make sure that all of our charging capabilities, if it's running at once, is 34 amps DC times 5. But for most residential, again, not to keep harping on it, but most residential systems like PV systems, off-grid systems, on-grid, the intelligence is built into the system. Okay, so let's talk a little bit about the battery protection limitations as well here. So we have the battery management system built into this, into each PHI battery, but that's definitely not something you want to rely on if there is an overcharging always happening. So that BMS is really there to protect against some extreme overcurrents. So if it sees something that's, if the breaker or the BMS sees something that's way over the battery's actual C/2 rate, that's where that protection comes in. Now, let's say you maybe have, again, let's say one battery and you're charging just right over that line, you're charging maybe, let's say 39 amps DC every day. Well, the BMS might not catch that. And doing this over and over can actually cause some damage on the battery. So just keep that in mind that the battery protection is really more there as a fail-safe for more extreme events. So it's not going to prevent it against continuous charging that's just always a little bit over that maximum. All right. So we just kind of went into this, but let's really talk about, what do we do to limit the charge rate? How do we make sure that we are sticking within these guidelines? Good news is charge rate is super easy to limit. We'll go into it later. The actual discharge is the harder part to limit. So charge controller being the best example of this, super easy. If let's say for this instance that we have 2 PHI 3.5 batteries. That's 34 amps DC per battery. And let's say we have a 100 amp charge controller. So maybe like a Midnight Classic 100. Well, we know that we can only charge the battery at 68 amps DC because we have 2 batteries. Super simple. All you have to do is actually just turn down that charge rate to output max 68 amps DC. Super easy with the charge controllers, no problem at all. The MPPTs are built for this kind of thing. They can definitely clip off what they need to, and no problems whatsoever. You might find that some charge controllers, like the Schneider, for instance, is actually a percentage and not a true amps DC. In that case, same thing. Let's say, again, we have the 100 amp charge controller, and I'm going to cheat here a little bit because it's super easy when we're using 100, and we have 68 amps DC. Well, we just have to divide 68 by 100, and we know that we have 68% charge. So just base it again. It's always going to be the same, whether it's a percentage or whether you're actually just programming in those DC amps directly, or maybe it's even kilowatts. Again, same design there. So if we're using the inverter's charger, we need to think in this case, we'll keep AC coupling to the back of our mind, so this next point here, but let's think generator charging or maybe charging from the grid. So if we're generating charging or charging from the grid, we're going through the inverter and actually converting into DC into the battery. Still super easy. We can just limit the max charge rate. Again, the example of being, let's say 2 batteries, just limit that charge rate to 68 amps DC in that case, if it's the 2 3.5s. So that tends to not be as much of an issue. Limiting charge is super easy. The only time it ever is maybe a little bit more challenging is when we're talking about AC coupled solutions. So maybe you have a grid tied inverter already, maybe you have micro inverters, whatever it may be, going into a battery based inverter and then into a battery. There's a lot of guidelines and they're far and from our own as well. So the inverter typically has their own guidelines as well. So if you're, AC coupling with like an Outback or a Schneider or whatever it may be, oftentimes you want to look into their guidelines. They might have a max size that actually goes into how much charging is going through, or really in this case, how much PV is going through the system. Your local jurisdiction might have code requirements specific for AC coupling. Not all do, but some definitely have some sizing guides that are requirements. Our guidelines really just fit back into what I've been saying is, if you have, let's say 3 kilowatts of PV AC coupled to 2 batteries, that's completely fine, because we know that no matter what happens, even if the curtailing or if the AC coupled function doesn't work exactly how it's supposed to, which oftentimes it's kind of I wouldn't say it's a newer science, but it's definitely an unperfected science a little bit. So if it does decide to dump that full 3 kilowatts into those 2 batteries, we know that the C/2 is still met. That max charge can handle it. And the last point I kind of want to make on AC coupling and really how it affects max charging is think about how your grid tied products interact. Not all are built the same. Some microinverters have just kind of been proven to work better with battery-based inverters and the actual curtailing. If you're within these guidelines, it doesn't matter. But if you are kind of working on maybe a project that's a little bit sized a little bit large as far as the max charge rate of the batteries with an AC coupled design, give us a call. I won't say any names of inverters I've seen that have had issues that are grid tied with AC coupling. But if you ever do need some suggestions, give us a call, and most of our techs know which ones to recommend. Okay. So now let's go into, we just kind of went through C/2. Well, really what we went into is current and how that affects charging with the Phi battery. But now let's go into what is the voltage and what does that have to do with charging the Phi battery. So first, the absorb and the bulk charging voltage. This is kind of, to look at bulk and absorb, or whatever they want to call it, and most settings tend to be bulk and absorb nowadays. There's less language now, but really what this is exactly what it sounds like. It's the bulk of the charging. If it's a bucket, you're filling up 80%. I once had somebody tell me that, if it's a bucket, you might be filling up 80, even 90% of the bucket during the bulk, and then the rest, maybe the absorb is that last, 10%, or maybe it's 9% and the float takes over a little bit too. So the bulk is really where the charging happens. We have some new settings that are going to be coming out. You'll see that it might say a bulk and absorb at 54.4 volts DC. If you're in tune with our batteries, if you've been installing these for a while, you've definitely probably been using something more like 56 or maybe even 57. That's not going to hurt the battery, but we are finding that we can use a lower bulk and absorb voltage of 54.4 to actually get the battery fully charged just fine. So less stress on the battery, why not? You know, we don't think it'll affect the life very much charging at that 56, but it can never hurt it to bring it down. If we don't need to charge higher, then we might as well keep it that lower. 54.4 is what engineering is now saying is an acceptable bulk absorbed voltage. And all the guides will soon reflect that. So it's also important, and this is kind of just snuck in here, and I apologize, this is my first time doing this presentation, so if something's out of line at all, that's okay. I'll just kind of get through it. So understanding the full charge and voltage reading. Now we're going to go all into, you know, SOC, state of charge, and the correlation with voltage. But it is important kind of just to touch real quick on it when we're talking about charging, in the sense of, you know, if we're charging, let's say 54.4 on our bulk, that's not what we would expect to be 100% charged. Resting state of charge is always going to be a bit lower. So, you know, when a customer might say, oh, well, my battery hit 54.4 and then I discharged a kilowatt and that was the end of my bank. Well, it might have just gone into its bulk stage. It does, by no means does it mean that it's fully charged when the charger is showing that bulk voltage. It's really what the voltage is when the battery has been disconnected from that charging source. And again, we'll go into that here in a little bit. So using float charge, this is a question that comes up a lot. I get calls about it. You know, engineering has definitely said we can get away with not using a float charge. It appears to be a little bit better on the battery. We've kind of come back with the real world team here at SimpliPhi has come back with there's certain situations where a float really makes a lot of sense. To me, off grid, a float charge, really any DC coupled situation, float's not going to necessarily be a big deal to use. If you're charging from an AC source like the grid and a battery backup, you definitely wouldn't want to use float. That would be a good time not to. Now, if you just want to not use it and you want to kind of get it in tune, we can even design our DC coupled systems, even our off-grid systems, to function without that float charge. Basically, what we're using is a high rebulk then, or a high recharge. So we want to trip that cycle at a higher voltage. So maybe, let's say and we'll get into the SOC stuff, but let's say we know 53.3 is fully charged on the battery. Maybe we hit that float, that rebulk or that recharge at something like 52.5, meaning that every time the battery discharges a little bit, it sees if there's solar available. This will make sure that when the night hits, the battery is at a good state of charge because it was utilizing all the PV possible. You know, this again, battery life, hard to say how it really affects it, but if you're off grid, I've noticed a lot of people just like to use that float charge. You know, I won't say there's a big problem with it, but definitely if you want to kind of learn the technique of just using only bulk, that 2-stage no float charge, it's pretty straightforward. You just want to set that high recharge. Now, if we're using a float charge, you don't want to set that rebulk very high. We'd want to set that lower, maybe 51 or 50 point, you know, whatever, 50, let's say 50.6, because we want it to be able to float for a while and not go through the entire charge cycle again until it really needs it. So that's definitely, there's going to be a big difference between that setting, and that setting is just really important in general. We'll talk a lot about that setting here in some of the last slides of this presentation. Okay, so now let's talk a little bit about inverters, the capabilities, the compatibilities, the integration, things like that. So again, I see a few things that might be a little out of place, but let's touch on them real quick. So voltage set points varying based on the inverter programming. This you'll see a lot. You know, maybe let's say you're programming a piece of Magnum equipment or a piece of SMA equipment. maybe a setting only goes up in certain increments, maybe 0.2 of a volt. This is where it becomes a bit confusing. So we try to build out these integration guides on our website for each separate product that we know people are integrating often with, in hopes of hitting certain. So maybe maybe your one inverter you use doesn't hit 54.4; it hits 54.6. So we try to set the integration guides up so that it reflects those increments. Now, the biggest one I see the issue is like Outback's a good example of this. I know you can actually set different settings, different increments in the Optics RE versus the Mate 3. So, it's always going to happen where a customer or an installer, whoever is going through a setting, and it's just a bit off from what our guides might say because they can't hit that increment. If it ever happens, we're not perfect. Just give us a call. We'll see if maybe we can update the manual or at least help you out and give you an idea of which, if you want to go up from that voltage that we have in the manual or down from that. Bulk and absorb voltage, most inverters can hit those. Again, there might be some slight 0.2 increments that we just need to adjust. And most of our integration guides we try to stay up to date with, so they should reflect those specific increments based on the inverter and the